The human brain is an extraordinary organ. It processes information through a complex network of interconnected neurons. Artificial neural networks, often called neural networks for short, draw inspiration from this biological marvel. They are designed to mimic the brain's ability to learn and make decisions. Imagine a child learning to identify a cat. They observe its features, sharp ears, whiskers, and a furry tail. Over time, their brain forms connections, allowing them to recognize these features and identify a cat. Neural networks work similarly. They learn from data, identifying patterns and relationships to make predictions or decisions. This essay will delve into the fascinating world of neural networks. We'll explore their structure, components, and how they learn from data. We'll also uncover their remarkable applications that are shaping our world. Let's embark on this journey of understanding these powerful tools of artificial intelligence. Neural networks are composed of layers: the input layer, hidden layers, and the output layer. Think of these layers as stages in a data processing pipeline. Each layer plays a crucial role in transforming the input into a meaningful output. The input layer receives the raw data like pixels in an image or text in a sentence. This data is then passed to the hidden layers. Hidden layers are the powerhouse of a neural network. They perform computations, extracting features and patterns from the input data. The number of hidden layers and neurons within them varies depending on the complexity of the task. A network designed for image recognition might have many hidden layers to process intricate visual details. Finally, the output layer delivers the results, such as classifying an image or predicting a stock price. Each layer in a neural network comprises numerous interconnected nodes called neurons. These neurons are the computational units of the network. They receive input from the previous layer, process it, and pass the output to the next layer. Connections between neurons have associated weights. These weights determine the strength of the connection. A higher weight amplifies the signal passing through, while a lower weight diminishes it. During the learning process, a neural network adjusts these weights to improve its accuracy. Think of weights as knobs that the network tunes to find the optimal settings for a given task. For instance, in recognizing handwritten digits, a neuron responsible for identifying curved lines might have a higher weight for connections receiving input from curved segments of the image. Section 4. Activation functions adding nonlinearity. Activation functions introduce nonlinearity into neural networks. This nonlinearity is crucial because real-world problems are rarely linear. It allows neural networks to model complex relationships and make sophisticated decisions. Two commonly used activation functions are ReLU, or rectified linear unit, and sigmoid. ReLU acts like a switch, activating the neuron only if the input exceeds a certain threshold. It's computationally efficient and promotes sparsity in the network. Sigmoid, on the other hand, produces a smooth, S-shaped curve, compressing the output between 0 and 1. It's often used in the output layer for binary classification tasks, where the network needs to decide between two options. The choice of activation function depends on the specific problem and the characteristics of the data. Section 5. Learning and adaptation, training neural networks. Training a neural network involves feeding it with labeled data and adjusting its weights to minimize errors. This process, called backpropagation, is the heart of neural network learning. Imagine teaching a child to ride a bicycle. You provide guidance and support as they learn from their mistakes. Similarly, in backpropagation, the network compares its output to the correct answer and adjusts its weights to reduce the difference. This iterative process continues, with the network refining its weights until it achieves acceptable accuracy. The learning rate, a crucial parameter, determines how much the weights are adjusted in each iteration. A high learning rate might lead to faster convergence, but risks overshooting the optimal solution. Section 6. Neural networks in action, real-world applications. Neural networks have permeated various aspects of our lives, revolutionizing industries and solving complex problems. In image recognition, they power facial recognition systems, self-driving cars, and medical imaging analysis. Natural language processing heavily relies on neural networks for machine translation, sentiment analysis, and chatbot development. They are also used in financial modeling, fraud detection, and personalized recommendations. The versatility and adaptability of neural networks make them invaluable tools in today's data-driven world. As research and development continue, we can anticipate even more groundbreaking applications in the future. Section 7: Conclusion and Call to Action. In this exploration, we've uncovered the fundamental principles of neural networks. We've seen how they mimic the human brain, learning from data to make decisions and predictions. We've also explored their diverse applications, demonstrating their transformative impact on various fields. However, this is just the tip of the iceberg. The world of neural networks is vast and continuously evolving. I encourage you to delve deeper into this fascinating domain, exploring different architectures, learning algorithms, and applications. Embrace the power of knowledge and join the forefront of this technological revolution. The future of artificial intelligence is in your hands.